Okay, we should be live. Hello everybody on YouTube. And okay, so yes, welcome to lesson 3 of object-oriented paradigms. As usual, the obligatory slide. We are live. The obligatory slide that we always have after Tom's intro, which is of course feedback. We do love to hear from you. You know the drill really if you've already been with us. If you're not on our Slack, get on there, it costs you nothing. If you've got a work Slack, don't worry, the Slack app happily will let you be on multiple workspaces and it just separates them with a little button at the side. And you just go to this slack.cpp.al, that's Alpha Lima, to register. So let's just quickly recap what we've learned in the previous lesson. It was mainly the finer points of C++ OOP, so usage of the static keyword. Of course, the static keyword is for having data shared between multiple separate instances of your class. We looked a little bit at the concerns revolving around sort of having a scalable design. Also touched upon in the first lesson where we said generally to prefer composition over inheritance. And of course, we learned how to build interfaces, because if you want a scalable design, interfacing things away is a great method for doing that. Should I say mechanism? I don't want to confuse the Java programmers. We obviously learned the virtual keyword. That is the key C++ language keyword that enables us to build what we are calling an interface. Unlike languages such as C# or Java, where they have an explicit language keyword for the concept of an interface, we don't physically have that in C++, but we can restrict ourselves and implement that concept by simply having a class and all of its methods are virtual, all of its member functions are virtual, and preferably pure virtual so they have no implementation, because then it is just an interface. So we learn the intricacies of that, how to put them together, how to then implement an interface, how to generify, and we'll be touching on that further today. Or at least those of you that did the exercises hopefully have learned to do that. So just to change it up slightly, I'm going to talk about OOP when it's gone horribly wrong. And a great quote, the object-oriented version of spaghetti code is, of course, lasagna code to many layers. Thank you to Roberto Waltman for that. Cheers. So we're going to finally get on to the diamond of death. It's a classic anti-pattern. It describes a form of inheritance, which I'm going to show you in a second, and it causes a whole raft of problems, which, well, I'll get into. The way in which it causes problems tends to differ slightly by language, and the languages can resolve them in their own ways. We have a way of resolving this in C++, which I'm going to get into. But firstly, this is the diamond of death. So to explain this, we have D here, which is the most derived class, as it were. So these arrows are pointing to what's being inherited from. So D inherits from B, and it also inherits from C. B inherits from A, so A is the base, the most base class. And C also inherits from A. And this causes a problem, specifically related to C++, is that the D class will have 2 copies of A. So when we construct D, it obviously it is a kind of B, so the compiler must go and construct the instance of B that D inherits from, and it must construct the instance of C that D inherits from, and that's all self-contained inside D. But then it looks and sees that these two, B and C, are also inheriting from A, so we end up with 2 copies of A. B has its own copy of A, and C also has its own unique copy of A. And this is because they inherit independently of each other, right? B doesn't know anything about C, and vice versa. So because of that, their inheritance to A means that it's completely separate and unique. You can, in fact, refer to it. If for some insane reason you created this, it will compile just fine. But if you want to use some functionality or data that is contained in A, you have to access it via a qualifier saying, oh, okay, I want to access B's copy of A, or I want to access C's copy of A. And it's extremely unlikely you would ever want to do that, have those 2 completely separate bases. So, as I've said, there's no way for it to actually know which one we want to use without qualifying it. So if I simply had, if we cut C out of the picture, so it was simply A, B, D, we could refer to stuff in A, and we wouldn't need to qualify it and say, oh, I want B's version of A or C's version of A. It knows because there's only one. But when you do this, there's two of them. But there is actually a way that we can work around this. But just don't do this. It's stupid. It's horrible. Just if you think about your design well enough, you shouldn't end up with an inheritance hierarchy where you've even put yourself in this situation. But somehow, if you discovered some code where someone else had done it and it was too big to realistically refactor because you didn't have the time, there's something called virtual inheritance. And what virtual inheritance does is it's a form of, deduplication. So let's get on to the subject. Again, as I already said, you should really avoid doing this. If you're designing something from scratch, you should not really be designing anything that requires virtual inheritance. But of course, if you're going to work with C++ and be a developer, you should obviously be aware of it. Who knows where you're going to get a job? Who knows what code you're going to work with? And not knowing one of these things is just going to be a detriment to you. The more knowledge you have, the better. So, in an inheritance statement, so as we learned previously, you can have class X, a colon, and then whatever you want to inherit from. So I might want to class A colon B, we inherit from B, or public B to inherit public B. Rather than simply just writing colon public B to inherit from B, we can actually write colon public virtual B. So when we declare what we inherit from, we don't just give its name, we put the word virtual in there as well. But when you're doing this to deduplicate this virtual inheritance using the virtual keyword, every class in your hierarchy that's going to inherit from it must utilize the word virtual. If they don't, they are not participating in the deduplication, and they will still get their own copy. So if 2 out of 3 classes use virtual that are using the same base, and you derive from all 3 of them, 2 of them are going to deduplicate. So they will deduplicate to 1, but the class that is not participating in the deduplication will have its own. And so you end up with a grand total of 2 of the base, right? The ones using virtual, they go down to 1. And the one that's not participating also gets its own. That's 2. So, as I said, it won't participate if you don't do it. So you need to make sure that you've used this virtual keyword everywhere. And this in itself makes your life hard if you're dealing with something, because you might forget to, and now you've caused a bug. So let's look at an example of it. We're going to have struct A as our base. This is a sort of code version of the diamond of death, if you like, but with virtual inheritance to kind of make it work. So we then have struct B, which is publicly inheriting from A, and it's using the virtual keyword to perform this deduplication. Of course, this has no effect if I only inherit from B, because there's nothing else duplicating it. So in the event that there's just A, B, and maybe a C, and that was a straight line, then virtual does nothing for you because there's only one of them anyway. But then we'll have a struct C, which also inherits from A. So B and C, they have nothing to do with each other, but they do both inherit from A. And also, in case anyone's wondering, I haven't put any code in these structs because it's not actually relevant to understanding the concept of inheritance. You can imagine whatever you like in there, right? The point is that these 2 are now saying, please, I want to deduplicate. So then when we have D, it publicly inherits from B and disinherits from C. D doesn't need to use the word virtual, right? Because these are separate classes. You could technically put it in there. You could use virtual everywhere if you wished on inheritance, but you shouldn't be designing anything so complex that you feel that you need to do that. So, in essence, because of the virtual here and here, this is going to see 1 copy of A, and it is no longer ambiguous. There is only 1 A in that hierarchy. But, as I've already said, preferably just don't do it. Stay away from it. Okay, on to enums. If you've worked with any other languages, these are a fairly common concept, and hopefully everyone should be fairly comfortable with them. And again, another great quote. If you want more effective programmers, you will discover that they should not waste their time debugging. They should not introduce the bugs to start with. Classic from Dijkstra. All right, so an enum is a way of applying, meaningful names to some values, some numeric values. And we typically group these in what we call an enum to denote some series of states. It doesn't have to be some series of states. It could just be, 1 to 10, but written as words. I don't know if you necessarily want to do that. It probably wouldn't make sense, but you can. There is one key difference, though, in C++ with regard to how C does it, which is that in C, enums make their values usable, but you don't have to explicitly refer to the enum. So much like a class or a struct, an enum can have a name, a reusable name to refer to. But the individual pieces inside that enum, so they're not quite data because each one just represents a number. But the names inside them, if you use a C-style, as we call it, C-style enum, they just escape into the scope. So I don't have to refer to the name of the enum. So if I was to contrast that, if I was using a class, I had class X, and X had a static data member called string. If I want to use the string, or access it, read it, write it, I have to do X : : string, right? It has to be fully qualified. When you use enums, C's style of enums, you don't have to do this qualifier anymore. You can just directly refer to the piece inside. But bear in mind also that enums are not like classes or structs. You cannot stick data in them. They just represent numbers. I can't stick a string in an enum. I can't stick it in any, and to prop it into type. So enums do not take up any space, essentially. A struct will take up space, an enum will not. So, of course, you can use C-style enums in C++, we have them. But since C++ 11, we've introduced this enum class. And we call this a strongly typed enum. And by using enum class, we now get the benefit of having similar behavior to a struct. We now have to use the name of the enum, : and then whatever element, as it were, in the enum, whatever state in the enum we want to refer to. And this obviously is safer, right? It's better if you can have a type that's not just sort of magically leaking its stuff out into a wider scope. Yes, they're completely compile type. Yeah. So here's a use case you might have for an enum. Let's say we have a traffic light. So we'll start off with the type safe one. So again, I'm calling the enum traffic light. Again, this class qualifier doesn't make it a class. It just so happens that when they were standardizing C++, obviously C++ 11, they didn't want to add a brand new keyword to the language just to support this. So consequently, generally speaking in C++, we don't like to add new keywords, because if you invent a new word that wasn't previously a keyword, and somebody was maybe using that for the name of one of their variables, it's going to be a pain for them to upgrade to the new C++, because it will fail to compile, because their variable's name has now become a keyword, and you're not allowed to use a keyword for the name of a variable. Unfortunately, there's some exceptions to that, which is final and override, and yes, we invented contextual keywords, but don't worry about that. I'm just going off topic now, really. So, obvious state for a traffic light is turned off. So by default, this off is going to be 0. It's going to represent 0. You can reassign it. I could have done equals 1. I could have started from 1. I've got no real reason to, right? I don't care about the underlying number the compiler's going to use to refer to it. All I care about is the actual name of that particular state. The compiler should take care of what number it wants to use. But it will be 0 by default. Red, this will obviously be 1. If I had set off to 1, so if I had off equals 1 here, this would just be 1 more, so it would be 2. Or again, I could manually assign it. I could do red equals 1. That would be silly, of course, because then off would be, if I'd have off equals 1 and red equals 1, well, they're the same then. Same number, that's a problem, but you don't really want to do that. So then we'll have red, yellow, green, yellow. Roughly makes sense, right? Decent use case. And then, in order to use it, we'll just have a variable, and we're just going to start it off in the off state. If you
wouldn't use auto, would it be enum as
no.
type?
If you wanted to state the type here, you'd use the word traffic light. So you'd replace auto with just traffic light. So traffic light state equals traffic light : : off. Make sense? So the auto keyword was introduced in C++11, and essentially it allows the compiler to do the work of deducing what the type of state actually is. So it has to be able to see that, which it can in this case. You can see on the right-hand side, it's off in the enum class traffic light, so the compiler can just go, okay, well that's traffic light then. But it can't be reassigned. So once it's deduced the type, that is fixed in place. I can't later put a string into state. It must always retain the exact same type it had at the point of initialization. So we are still type safe, as it were. So now let's have the C style. So again, we've got enum traffic light. And I'm not saying that the C style is necessarily bad, right? It can still have its uses. It's a bit ugly if you're putting it in headers that are going to be shared, because you're going to pollute everyone else's code with your enums members, which is a bit ugly. So enum class is preferable because of that reason. But if it was internal to you in one file, you might not mind. And again, all the same stuff, and you're still allowed to do equals 5 or whatever number you like. It must be a number. And then it's a bit simpler now because you can just put off, which does look quite nice. It's quite tempting to use this for this very reason. It does depend on the placement of the enum itself. Where is it going to live? You don't really want to pollute loads and loads of code with this enum. If it's constrained to a small portion of code, it's probably okay. But again, yeah. Question, yeah.
When you activate, can it take more than one state at a time? The enum, can you have one, define one enum, and it has more than one state?
Oh, right. So the enum is just defining the possible states. The enum doesn't exist in terms of it doesn't exist as any kind of value when you run the program. You have to create something like a variable to represent a given state.
Because I've seen one interesting use case for command line applications where you would have, for example, the task text. So every enum.
I know what you're talking about.
Well,
so what you can do. So the problem is that yes, you can do a bitwise OR, right? You can have a set of enums, and then you can have like this wouldn't really make sense for a traffic light. Sorry.
You need powers of 2 generally.
That's exactly, yes, precisely what I was going to say. So as it stands, you couldn't use it in the way you're describing. So normally you do a bitwise OR. So imagine I wanted to get rid of red, yellow, right? So I could instead sort of do red or bitwise OR with yellow, right, to sort of mark the flag. The problem is that if you, obviously it's going to be what, 0, 1, and then if we got rid of this, it'd be what, 0, 1, 2, 3. So it'd be 1 or 3, which is a problem because 1 or 3 is just 3. It doesn't add the data. So the way you get around this is you manually assign to every element with 1 left shift and then an incrementing number. So the first one will be 1 shifted left by 0, the next one will be 1 shifted left by 2, 1 shifted left by 3, 1 shifted left by 4, etc., etc., etc. So that now they occupy an individual bit in memory. You could technically not use the shift operator, it makes it more readable, and you could just double every time. So you do equals 1, equals 2, equals 4, equals 8, equals 16, right? 1, 2, 4, 8, 16. You could do that if you wish. It's probably a bit less readable than using the shift operator when you get to large numbers. I don't know how far you can double up numbers. Yes?
Should you have an on state that doesn't have a colour association?
Yeah, you could. I mean, this is really just an example. I haven't built a traffic light before. Yes, you could. Maybe you need to represent the on state, or maybe you could say, well, actually, we'll get rid of the off state. We don't care if it's off. This enum's only concerned with when it's in operation, and there's only these possible combinations, right? You know, you could argue that maybe off is a foot gun. You might accidentally set it to off and turn it off in the middle of operation. So,
can you reassign the states?
Yes, absolutely. Yes, you can. So as long as it's not const, if you had const auto in either of these cases, it would obviously be fixed. But because it's just mutable. Yes, you could assign it here, and then the next statement could be state equals traffic light : green.
Yellow. Can you print them to the output, like C out, extraction?
So if it's the weekly type enum, yeah, it'll just work. It'll display as a number though. It will not display the word. It will display just the number that represents it. If you use, sorry?
C# often does prints the off.
C# does. Hopefully we'll get some form of reflection eventually in C++ to let you do this. There are scripts, I believe Boost has something to help you along with doing this for enum, but in pure C++, no, it just prints a number. This one is a bit more complex because it's what we call the strong typed enum. It won't just print it. you'd have to cast it to an int or to a char or some value. That can help you though, because if you do want to print it as a string, you could easily just have an operator overload that will take an instance of a traffic light, so it takes state, and then you just have a switch case, right? If it's off, print the word off. If it's red, print the word red. Da, 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 da. The problem is it's a bit boilerplatey having to write that. Yes?
You would have to define the operator overload globally. You would not be able to do it as a member of the
Correct, yeah, it needs to be both.
If you have two enums, the second one has the same, you cannot have the same word off, right? Because you do not know which one is the best.
Precisely, which is why this one is why this one is better, because obviously it's scoped specifically to off. It doesn't pollute the namespace, right? Yes, if you have two enums and they're sharing these values, or you even maybe have a macro, right? That could be nasty. So yes, prefer these precisely because they don't escape, and you must use them fully qualified. They don't. It can't. There's no chance of these treading on each other if you have two of them. Okay. Any? Oh yeah. Sorry, go on.
On the left-hand side, is an alternative way to do it, or is it on the old way?
So the new way is the strongly typed one, the using the class keyword. It's not a class. It's just the qualifier that we recycle the word class. Yes, this is the best way. This is the sort of old way. And again, they're not necessarily bad, but you should sort of restrict where you use them. The primary motivation for this was that if you're going to stick an enum in a header that lots and lots of people are going to use, say as part of your library, you're giving them something that is not going to pollute their code. This one will pollute. This one's going to pollute. Because as you can see, right, I didn't have to qualify it. I just wrote off. It just works. Okay. No further questions? Yes? No? Cool. Okay. Yeah, go
If you
on.
want to change the state, you have to do some kind of testing.
If I want to change...
Take the value that you want to see.
Yeah, so...
I want to move from off to green.
Oh yeah, so that's actually a good question, the second. There's something I didn't get into. So, with the safe one, the type safe one, you need to static cast it to an int, char, whatever. And to go from a number to the enum, you also need to static cast it. There's one little caveat to that, which is that as this stands, right, there's only 0, 1, 2, 3, or 4. Sorry, 0, 1, 2, 3, 4. Yeah, there's only 0 to 4 that's valid, right? So as long as I static cast a number in the range of 0 to 4 to a traffic light, that's fine, because it's in the range. If I go one above that, that's now undefined behavior. In most compilers, you probably get away with it, but it is in fact undefined behavior to go beyond it. However, you can get around this. You can put a colon after the type name before the curly brace, and then give it a size, and the size meaning an int or char. So you can do colon char, and now you have a valid range of whatever char's limit is, right? So negative 127 through to, I think it's 128, something like that. Or you could use an int, then you've got like 4.2 billion. That doesn't mean that everything outside of that range now just has a magic name. It will not, but it won't be undefined behavior. So for example, if this was int, right? If I cast 2 to a traffic light, the number 2, then it will obviously be red. If I cast 4, it will obviously be yellow. If I cast 500,000, it will be none of these still. It will be absolutely none of these. It will not compare equal to any of them, but it won't be undefined behavior. The compiler will allow you to do it because it guarantees that there is enough memory to store that large number, yes.
I don't understand what static casting is.
Crikey. Yeah, so static cast, you're familiar with the concept of a cast, first of all?
No.
Just casting in general. Okay. So, generally speaking, you don't actually want to cast things around. You want to avoid casting as much as possible. So, casting is where you say, I know I have this type, but I want you to turn it into a different type. So this can be sometimes reasonable. I might have a class, right, that has a conversion operator that returns true or false, so operator bool, basically, right? And sometimes you make that operator explicit. And usually if you have a class that's not actually Boolean but has some true or false flag to say, oh, I'm in a good state or a bad state, for example, you may not necessarily intentionally want to cast it to a bool, right? So by making the conversion operator explicit, which hopefully you saw from last week, by making the operator explicit, we can't just accidentally do bool b equals instance of the class. It will say can't compile because it's explicit. But if we do actually genuinely want a bool, we can use static cast to bool to say that no, we explicitly want you to do this. So casting is saying, I have this type, but I'd like you to turn it into some other type. And there are 3 levels of casting. There is reinterpret cast, which is where you tell the compiler, I know much, much better than you, just make it this type. There are some ways in which it will still prevent you doing something incredibly silly. So for example, you can't cast a non-pointer, or you can't reinterpret cast something that's not a pointer to a pointer. But the point is it allows you to essentially violate the type safety. You can use reinterpret cast and go from pretty much any type to another type, and you'll probably just crash horribly. For example, I could cast a pointer to an int to a pointer to a stood string. It's obviously not a stood string, it's just going to crash horribly.
So long as the structure is the same, you'd be okay, right? If the structure of each class is comparable.
So the question was, as long as...
The byte order
Yes.
of the data in memory is the same.
So the question was, as long as the structs happen to have the same exact data, it will be fine. And the answer is no, and yes. So the real answer is no, because it is completely undefined behavior to do that. If I create 2 classes, and a good example of this is especially if you happen to use different compilers, it will all fall apart horribly. But if you have 2 different types, and you cast from A to B, but they just happen to have the same data, that is completely undefined behavior. There is no guarantee made by the standard that that will even work. Yeah, you might get away with it, but you're not actually allowed to do it. It's a very common thing that people have done for a very long time, but strictly speaking, no, you're absolutely not supposed to do it. And also where it can go horribly wrong is if it's a simple struct, right, it might be okay. If it's got virtual member functions, then that will start to fall apart.
So why are you saying not to cast when
So
it's a
don't use,
different class?
yeah, so don't use reinterpret cast. That's something where you think you know what you're doing and probably don't. There is then static cast, which you generally use when you have, say, a base class, an instance of a base class, and you want to cast it to a derived class because you happen to know better and say, oh, actually, I know what the implementation really is. I know which kind of base this really is. Again, it's a bad design because you shouldn't need to know about the derived class. You shouldn't need to be using the derived class. The base class should be good enough for what you need to do, and it's designed for if you need to do it. But again, static cast is you saying, I know which one it is. If you're wrong, it will still compile. Again, you probably have weird undefined behavior. It'll all go horribly wrong. But if you happen to actually know, you can do a static cast from base to derived, and it will still work. And in the case of an enum, it's obviously fine. Static casting an enum to an int is okay, and static casting an int back to the enum is okay as long as traffic light was declared as being the size of an int, because then it will fit. And it won't let you do random things. Static cast won't let me say that let's cast an int to a stood string. It's just they're considered physically incompatible, so it won't let you do it. So static cast is a bit safer. Finally, there's dynamic cast, and I should have made some slides for this really. Probably next week. Dynamic cast will essentially do a runtime check, so it's not free anymore. But it says, okay, I want to try and cast from the base to the derived. And if you use a pointer, so give me a pointer to the derived, it will either give you back a valid pointer or null pointer, so you can just check, did I get null pointer? Okay, I was wrong, I can't use this. If you use a reference, if you say, please cast this reference to that reference, so base to derived, it will throw an exception if it's not actually compatible. So you can use pointers if you don't want an exception, and use a reference if you do want an exception. Right.
So what did you say? If you did int,
Sorry?
colon int, and you went to 5,000, will it give you a 0 back? Or would it...
No, it will still be 5,000. It will preserve the value, but none of your names actually represent it. So it's completely valid, but you have no way to actually directly refer to it. You just have to cast it back to an int to see what it was. Yeah. But it could be useful for like a default case, right? I have a switch case, I have a case for off, a case for red, blah blah blah, and then I have a default case for everything else.
If it's anything else.
Yeah. Precisely. So on to operator overloading, and of course, any fool can write code that a computer can understand, but good programmers write code that humans can understand. Martin Fowler. So, helping your fellow programmer. Operator overloads are essentially a way for you to provide convenience. Convenience for yourself, convenience for other people. So if I have two strings, not two cows, being able to use A equals B, if I want to just compare them, it's quite convenient, right? Nice and short. It's much shorter than doing A dot equals B, like you would in, say, Java or C#. It does the same thing, right? Dot equals is a function, it returns a Boolean. I can do if A dot equals B, yeah? It's a lot more easier, a lot more idiomatic. If I just do an equals operator, everybody knows what that means generally. In most programming languages, it's just an equals. So C++ gives us this defined list of what operators we're allowed to overload. But don't just overload anything. There's ones that are, ones like equals, it's fairly obvious what's going to happen. There's ones that you can overload that people will use anyway, but you can cause unexpected behavior. You can surprise other developers, maybe even surprise yourself. So for example, operator comma. Yes, you can sadly overload the comma operator. That will, you can implement your own behavior, but someone's going to probably accidentally use A comma B and get, well, completely not what they thought would happen, right? Usually if you use the comma operator, we take what's on the left, discard it, and turn the right. And operator ampersand, this is also another badly confusing one. I'm not referring to the, obviously the bitwise AND operator, that might make sense, but the one for taking the address of an object. So if I want to get a pointer to a type, so a pointer to my type, if I've overloaded this one, this is the overload for taking the address, that could be horrible, right? I might return some other random object, and they don't actually have the address of my object anymore. They've got something completely different. So these are a good example of what you shouldn't overload. And just think of these overloads as just something that as functions. Operator overloads are simply functions that the compiler is going to look up when it sees that someone's using that operator. So for example, for the equals, all that's really happening inside the compiler is it's saying, okay, well, you used equals, you've got your struct or class type. So is there a function in the class, like the call, that implements the equals operator? And we'll see shortly from the syntax that the actual operator, the name of the operator overload function represents what it does. As well, you can see from those other ones. So, when you're creating these overloads for your class, there are essentially two basic ways of doing it. You can do it as a member function, just, have it literally inside the class. It makes your life easier probably, because if it's a member function, it's part of the class, it can access private data and all that good stuff, no problem. And it's usually what you want to do, and it is the easiest to implement. Of course, there's exceptions, but usually start with a member function. If you find that it's in some way limiting its usefulness, you might want to break it out into a free function. So obviously a free function is now not part of the class. It's just a standard function that will take however many parameters are needed for the operator. And obviously this might make sense for operations where you're dealing with sort of two completely different types, and somebody might swap the order of comparison. So if I have an instance of A equals an instance of B, then if A has the comparison operator, I always have to have A on the left for it to find it. But if I have a free function that's not a member for implementing this comparison, it doesn't matter which way around, which side of the equals the two types are on anymore.
Could you overload both class functions?
Alternatively, you could, of course, implement it by writing it again in another class, but now you've had to write more code, which is a bit of a pain. So in this case, you might need to make the free function a friend of your class, because it might need to access private data or protected data. But again, operator overloads are just functions. The compiler is just doing a lookup. They are not anything magical. It's just a lookup. Say, oh yes, call that function. The function has a return type. The function takes arguments, right? They are just functions.
Sorry, I'm getting. Could you use inheritance to solve that problem? Just writing that when you're comparing two classes.
You could use a template function, possibly to solve the problem.
Okay.
You can have a templated operator overload, which can then punch out whichever versions get used. So they are just functions. You can call them directly by their full name. So if I have an operator equals equals, I can literally directly write operator equals equals and call it that way. It's a bit silly. It's much easier not to use the word operator and just put equals equals. But I can. Nothing's stopping me. If I do call it by its name, I have to call it with the exact same syntax as a normal function. Operator equals equals, open parentheses, the arguments, close parentheses, like a normal function call. And again, if they're a member function, if they are a member of your class, again, they act just like a regular one. You can call that too inside your class by its full name as if it were a regular function, because it is. So let's have a look at a convenient class, and we're going to look at a semi-smart pointer that I've implemented. So for simplicity, obviously for a smart pointer like the ones we have in C++, to be useful, they should work for any type. This one I've not done that. I'm not using a template to keep it simple for you. It's simply going to be a semi-smart pointer for an integer, an int. And hopefully we're going to seamlessly cross over now, if I can move the mouse. Woo. Cool. Right, so don't worry about the include. We've declared our class smart int pointer. So obviously we need to manage the underlying raw pointer, right? The thing that we're going to manage the lifetime of. So I obviously want to, oh no, where's the mouse gone? Okay, I've lost the mouse completely. Can I use the keyboard? Okay, I can use the keyboard, that's fine. Right, so this is obviously just a raw pointer. We're going to start now on public data. Well, we want a default constructor. Obviously I need to explicitly restore it, because as we learned last week, if you have a constructor taking arguments, it will suppress the default constructor, so this brings it back. And of course, if you use the default constructor, we initialize this to nothing, to a null pointer. So we then have an explicit constructor. It again takes the raw integer that you've constructed, and it just copies the pointer value, not the value underneath, but copies the pointer into here so that we can track its lifetime, or manage its lifetime. This is the move constructor. I did get into special constructors in the first lesson, but essentially this is, we don't want to let someone create a copy of our smart int pointer. We want to only let them move it around, not copy it around, because obviously when its life ends, we delete it, and you can't go and delete an object twice, right? I can't delete a file twice. After I've deleted the file, it's gone. If you try to delete a pointer twice, you will crash. So we allow you to move the object around, but not copy it around. Because if you copied it again, we'd end up calling delete 2 or more times. So yeah, as I've said, the destructor kills it. Now for the convenience bit, the bit that is relevant to this section. Operator equals equals. It's a member function, so it returns a bool, because obviously if it's equal, we return true. If it's not equal, we return false. We can take a const reference to our own type. So we're going to have the one instance is us, right, on the left-hand side, and then the other instance is some, again, our own type, some other instance of it on the right-hand side. Made it const accessible. We don't need to change anything, so we're going to use const because we're just comparing. And we promised we won't throw exceptions. We've got no reason to. And of course, we just compare the value of the raw pointer. So don't forget, this is managing the pointer. It's not tracking the value inside. So is the raw pointer in us equal to the raw pointer in the one on the right-hand side of the user's statement, the programmer who's using our overload. And an example of how you would use it is simple, right? You have smart int pointer declaration for A, and then so there's one instance called A, there's another one called B. A has nothing in it, B has an int in it that we've set to 5. And then of course you just do if A equals B, and it will just look up this function. Done. Similarly, maybe we want to be able to just compare our pointer to a raw pointer rather than our own type. So we have a separate overload. So now you can just give it a raw pointer, and we'll check again. Is it the same one or not? I did throw one template in here, just to be a little bit clever, but if I could get the mouse to work, I would, oh, well that just took over, didn't it? Let's try that again. Oh, cool. Okay, so click. Yeah. So we have one template function just to show off. So this is operator not equals, right? So it's the inverse of operator equals. But you still have to implement it. Just because you've made one for equals doesn't mean it magically generates one for not equals. So just to show how templates can be useful, we have any type T, and all we simply try to do is we call operator equals equals. So like I was saying, it's a regular function. You can call it. So we're calling operator equals equals and giving it the argument of whatever's on the right hand side. And then obviously we invert it with the exclamation mark. So if this were to return true, we invert it to false. False to true, of course. And now I've got one template that will work for both of these, because if they pass a raw pointer here, this is going to resolve to this one. And if they pass us a smart int pointer, it's going to resolve to this one. So just a saving writing that twice.
So I don't understand what's right hand side comparing to.
Us. So this is a member function, so we have this. There is an implicit this in this. So which is why you're allowed to use raw pointer here. Right? Because it's our member raw pointer in our instance. So again, I've got an assignment operator now. So again, we only allow you to move stuff around. So first of all, we call the destructor, accessing it through this pointer, because if we currently own an object, we need to release it before we replace what we're pointing to. But afterwards, we set ourselves to the other side's raw pointer. We've taken ownership of it, so we just set theirs to null pointer.
What happened if you didn't delete it? You forgot.
You'd leak it. If we didn't call the destructor here, we just leak the memory. So, bearing in mind that calling the destructor like this is actually something sort of, how can I put it, a bit smart-ass. So, I know what my destructor does, I wrote it myself, right? So I know that it's safe for me to explicitly call it in here just to get it to run that piece of code. When you're outside of your class, or you haven't written your own destructor that you know is sensible to use, don't actually call this like this. The compiler does call the destructor for you generally, right? When we actually destroy this object, so when the compiler when we are operating here, we call the destructor. When the compiler is also getting rid of us, it will call it again, which is fine because obviously we've got rid of our old object and then replaced it with a new object. So when it does call our destructor to really kill us, that's fine. It will just clean up. So again, if you look at the comments, these are all examples essentially of how to use it. You could have a const smart pointer here, a and b, and then use not equals. For the assignment, we'd have an a and b, and just use std move on b to invoke this function. Similarly, for this one, we can now take a raw pointer as well. Convenient, right?
What's the reference?
That's an R value reference. That's what you have to move from. You move from something that's temporary, as we call it, something that we're going to kill. We're going to steal its content. So, again, another one for a raw pointer, very similar, except we're not operating on. Except we're not obviously not operating on another instance of ourselves, it's just raw. So there's nothing else to destroy. And now we have, for convenience, not a dereference operator, the operator star, right? Because if you have a regular pointer, you usually want to access the value inside it, the value it's pointing to. So we can overload operator star. And it's fairly simple, we just return star raw pointer, right? And it's going to be an int reference. So, for example, I can have a, which is got a pointer to an int, it's initialized to 1. And then I can take a reference to the value inside the pointer by just dereferencing it as if it was a raw pointer, because I've overloaded it. Similarly, if it's const, I can give them a const reference to an int. So obviously if I had a const raw pointer, I need to preserve those semantics. And again, we can do the same thing here. Of course, this is different because this is taking a copy. If you have a constant, I can't modify it, but I can take a copy of it. So
on the line 49, yes, for example, you have int and then ampersand, yes?
In ref, yeah.
In ref. But you're returning the pointer. Why is that? Why it doesn't?
No, I'm not. I'm returning the value inside the pointer. I'm dereferencing raw pointer.
So if I want to return pointer, yes, just do people return the pointer?
If I wanted to return an int star, I would just return raw pointer. I wouldn't return dereference raw pointer.
Oh, okay. So that's the difference.
Because raw pointer is an int. Raw pointer, that is the pointer. Right, I'm getting the value inside the pointer.
Yeah, because it's dereference. Yeah.
And then this is slightly messy. So I think I wrote at the top that technically speaking, if you had an array of ints, this would be wrong. So, but we'll brush over that for a second. You can also have a brackets operator. This is exactly what std vector gives you. When you use those square brackets on a std vector or std array, it's just calling an operator overload. That's just in the standard library. So for example, I can have an array of integers, and then and because my smart int pointer is overloaded on the array operator, I can just do second element, right? Because obviously the first element here would be 0, because elements is numbered from 0 upwards. So this is the second element, of course. And I can just set it to 12. Easy, done. Of course, there's no safety checking in here. If you go out of bounds, you'll just crash the program. And then, of course, similarly, we have one for a const instance. If you have a const smart int pointer, we again can copy it, or we can have a const reference. We can't modify it because it is constant. But taking a copy, of course, is fine. And then we have an operator bool. So this could be useful in if statements, right? So I have a smart int pointer, const accessible, of course, it's just read only. And we can just do if a. So this is really for checking if my smart pointer is owning an object or not. So for example, if I had this one here, this one clearly has an object in it. We put an int in it, a new int. This would be true because raw pointer would not be null. But obviously, when we default construct, we explicitly set or we initialize raw pointer to null pointer. Well, it would be false. So it's true if it's owning an object, it's owning an int, and it's false if it doesn't own an int. And this is exactly what unique pointer does. You can check if a unique pointer is holding an object because it has an operator bool, conversion operator, as it's called. Is that clear?
There's a lot of information.
Who's the explicit?
Yeah, so I did cover the explicit keyword, but just to briefly touch on it essentially, it means that it won't implicitly convert to a boolean, so I couldn't do like bool b equals some instance of my smart int pointer. I'd have to static cast it, as I was saying earlier, to say that yes, I really want it. The reason it works in if statements is because if, while, and for, the loops and the if statement, those are special. The language states that if you use a type, some kind of object, some class, some structure, if you use that in an if statement or a for loop where you check the condition, or a while loop where you check the condition, it is allowed to just find the explicit. It's allowed to find this and just use it for those specific cases. If you try to create a bool, bool b equals some instance, that one requires you to cast it.
I'm not familiar with this standard pointer difference.
Oh, that's just correctness. I mean, it's not really relevant to using this operator. But essentially, the reason why I chose it is because obviously raw pointer is a pointer, right? And the standard guarantees that the maximum and minimum numbers of this will be large enough that you can go all the way to whatever feasible amount of memory you're going to occupy is. Just a number though, really. It's just a standard. It's a standard library type, but it's really just a number. Right? If you're on a 64-bit platform, it's probably just a one-signed 64-bit or signed rather. Okay, so we've. Yeah, do you want to look at the code again?
Well, yeah, you can go back to it. Can you do it with any type? That you overload the type function?
Which one are you referring to?
The bool.
Cool. Yeah, you can. You can have a conversion operator to any type you like in the world. You can have an operator stood string, operator int.
Does it at least have the decency to show you when you're giving the wrong return value?
What do you mean?
For example, if you overload the bool and you're not returning.
Oh yeah, that won't compile. So if I say that I want to be convertible to a bool, that's also stating the return type of my special conversion operator. So yes, you must ensure that your return type matches whatever this is. But again, this is just like a function. You can call this if you want. So back again. Right. So we've seen a bunch of code. Was there anything in there that wasn't clear that you'd like me to go over again before we move on? Tumbleweed. Okay, cool. CRTP, the curiously recurring template pattern. And a great quote which really fits this. The nice thing about standards is that you have so many to choose from. So, there we go. Virtual, but without it. So CRTP, yes, was originally devised, just because people didn't like the cost of using the virtual keyword because it involved at runtime having what was called a V table. Because obviously if you have this inheritance, this polymorphism, right, a piece of code doesn't necessarily know what implementation it's going to call. And because it doesn't know, previously compilers had to generate what's called a V table. So you would have an implementation, it would put some pointers in memory to its actual implementation functions. And then when you call the function that only knew the interface, it could simply be given this table and say, right, well, here's the list of functions you don't know what I am, but you just want to call maybe, change traffic lights, disable, enable, right? It knows the signatures of the functions it wants to call, it knows what arguments they need, it knows what they return, but it doesn't know where they are because it doesn't know the implementation, it knows the interface. So the implementation just sets up this table at runtime, and then all the function that takes the interface has to do is go, which one do I want in this list? I want the enable function. Okay, let's grab its pointer. Obviously this is all assembly code, but you can just grab the pointer for that, fill in the arguments, dispatch to the pointer, and then the CPU is going to jump to wherever that lives in memory, which has an implicit cost. Because if the compiler could simply see that, it wouldn't have to set up a table in memory. It wouldn't have to have this dispatch table. So we could save some memory and save the compiler having to do this indirection of loading the correct address into its register and then jumping to it. In the assembler code, it would simply just be, well, I can see where you want to go, you want to call this function, jump here, done. So it was more efficient. But that's the old days. And it's rarely a concern. It still can be sometimes, it depends on what you're building. If you're building a library where it's crossing a boundary, then it would be impossible for the compiler to avoid the virtual table. But similarly, if you were doing that, CRTP wouldn't help you anyway. Firstly, computers are a lot faster though. Okay, maybe your compiler does generate a V table. We've got hexacore 3 whatever gigahertz CPUs these days. Does it really matter in what you're doing? It might do if you're doing something like HFT, quite possibly. But even if you are doing something like high frequency trading, compilers have got a heck of a lot smarter. And we'll get into that shortly later as well, but not too much. So this concept does rely on templates. And that means it's completely compile time, right? There's nothing happens at runtime, whereas virtual could happen at runtime. Again, previously it pretty much did always happen at runtime, but these days sometimes it can be avoided. CRTP is completely compile time. But again, if you were building a library and you were crossing a boundary, so somebody was going to use your library separately, they were going to download it, build it, and then they were going to just run with your DLL. That's crossing a boundary. So you'd still have to use virtual in that case because it's runtime. Generally speaking, just stick to using virtual. Maybe you have a justification for using the CRTP. You should definitely check your compiler if you're using the latest and greatest. You will probably discover that you don't actually need to because the compiler's so good at optimizing, it can see through all the virtual and figure out where to dispatch and inline everything. So if you're going to use it, base it on evidence. So let's look at a sort of approximate comparison of virtual versus CRTP. Again, curiously recurring template pattern. So we'll have a struct base, stick one function in it. It's obviously got the virtual keyword, const char star name, const accessible, equals 0 to make it pure virtual, which means it has no implementation. Somebody else must implement it. So this guy's going to implement it. Derived is implementing the name function. And obviously we have the override safety check. Again, it will compile just fine if you don't include the word override. But by having the word override, if we somehow screwed up the return type or we screwed up the name, the compiler will tell us that we did, well, screw it up. And we'll just return our name as, well, our name's derived, so return that. And we're pretty much done, right? So this is fairly simple. If I take a reference, if a function takes a base, a reference to base, or a pointer to base, but we actually gave it a derived, when it calls name, it's going to get this. It's going to use the virtual dispatch to find the implementation. So now with CRTP, we're going to achieve sort of the same thing, but again, it's all compile time now. So we'll have our struct base, and this is where it's going to start getting messy. Again, now it's not virtual, of course, because the whole point of CRTP, at least one of the motivations at least, is you don't have to use virtual, so of course there's no virtual. But otherwise it's essentially the same return type, still const accessible, same name. And now here's where we get a bit messy. So the template type T is going to be whatever implements us, or derives from us is more accurate really, because then that's truly implement. And we have to static cast our type, our this, to the type of whatever's deriving from us. And just to make it a bit more readable, I just stored it in a variable. Yeah, you wouldn't have to. And then of course we can just return the name, whatever the name function from that implementation gives us. Okay. And we end the struct. So now let's look at how we derive from it. This is where it's getting freaky. This is what makes it. This is the CR. This puts the curious into curiously recurring template type. We have a struct derived. This is a template type, so it's got some generic type you need to fill in to punch out the template, like the cookie cutter. So the template type is us. It's actually us. So we have an instance of base. We're going to cut out from the template. We're going to punch out from the template a base which has derived filled in for t. So t is now derived. So when someone calls name, what actually happens is t is in fact derived. So we're static casting us to that, which is legal. It's fine because we do actually derive from it. Static cast will compile. And of course, we now need to match that. So because this is calling name, this needs to be called name here. You could technically make it different. It's probably going to make your life harder because you've now got to think about what's going to where. So for consistency, we've chosen to use the same function name. If I change this to not name, that would have to be changed to not name. But that's probably silly. You probably don't want to do that. And again, we just return derive. That's it, done. And then close off the struct. And that is basically CRTP. You have a template type, and then you specialize the template class on your type. As you can see, I think everyone would agree that virtual's a lot easier to understand, I hope.
Yeah, but you can only use chars for virtual, and with CRTP you can only use chars as well, because it's. Why do you, I don't understand why you need a template. If you've got a template, you're only dealing with chars, aren't you? Char stars in the base.
Yeah.
Derived.
No, that's just the return type of the function. It's irrelevant what that is. That could have been a std string. That could have been an int. Could have been anything. It's not. For the purposes of the example, this is the return type is irrelevant. It's not part of the example. It could be anything. I just chose that because I thought it was easy to show something semi-meaningful.
Yeah, but doesn't the template make it more sort of flexible on your?
Well, no, because I'm not using the template type there. I'm using the template type there.
Okay.
Again, so base is specialized on derived. So that means t is now substituted for this type, my struct type. So we're just going to say that our own type, our own instance, is actually not an instance of us. It's an instance of this guy. Casting it to a pointer to this
So it
one.
seems you're using a template, which should cover all different types, and then dealing
Well, it
with
can.
one specific type.
Yeah, I
to
can.
return. So why do you need a template in CRTP? Can't we just remove it?
It's literally called curiously recurring template pattern.
That's why you have to use templates.
Well, I mean, the point is that it's dynamic. It's not dynamic dispatch really. The point is that I can have something that's also templated, right? So it takes an instance of base t. I can substitute in derived, and when it calls name or whatever, it will still go through this pattern to dispatch down to derived, right? But it's all at compile time, right? So you avoid the overhead. But it's also, well,
Okay, that's why
ugly and more complex.
That's why you need a template to go to.
Yeah. So, well, let's just summarize CRTP really. Clearly, as you've seen, it does not map one-to-one with the semantics of virtual, which is a really good reason to just not use it, preferably. And as you saw, it also requires you to do this ugly static cast thing, which probably isn't really that friendly to you. Again, the thing of CRTP is I'm including it primarily because it's something you should be aware of. This does get used. It absolutely does get used. And so not knowing would be to your detriment. And as I said, it's way easier. It's way easier to understand what virtual is doing, and especially if you forget to implement a function, right? You're doing it with a load of template errors if you're using CRTP. It's like, oh, what's this? You can't call it because there's no such thing as failed instantiation. If you use virtual, now it's just saying, oh yeah, sorry, we can't compile this class because this thing could be a virtual and you didn't actually implement it. That's a lot shorter and a lot easier to read. So, yes, CRTP does potentially avoid this cost of virtual dispatch, this extra work the CPU has to do at runtime. accepts that most modern compilers are capable of this concept that we call de-virtualization. So the optimizer looks at all your code and it tries to see through the hierarchy and see, well, this takes an interface. What are you actually giving it? Are you giving it this implementation? Well, cool, let's just substitute out virtual dispatch and just plug it straight into the place where the code is for the implementation. And that means that you don't pay anything at all. Now you're using virtual, it's just as efficient as using CRTP. And you've got nicer code. You've got more readable code.
Which compilers do that?
So currently Clang has it, GCC has it. I can't remember which version of GCC introduced it. It's documented somewhere. If you use the latest and greatest compilers, then you can expect to get it. Microsoft, I believe, have it, but then again, they might be working on it. You'd have to check for Microsoft. Tristan looks like he wants to say something.
They all do it. The difference is how clever they are about doing it. They all do it in some really simple circumstances. So if you just have like an object on the stack and you can see the static type there, and you call it a virtual function, it will call the right version. It knows the static type of okay. We all compile to do that. Clang and GCC in particular will do very, very clever things, like basically guessing which the right things probably got, and optimizing to say probably going to have one of this to the right side. So optimizing that case. So yeah, they all do something. They all do simple forms of de-virtualization. The newer, more advanced compilers.
So, well, that's a different thing. So you talk about speculative de-virtualization. There is also speculative de-virtualization where the compiler just adds some optimized code to make a guess and hopefully it's right. Generally speaking, if you want these benefits of having proper de-virtualization, just use link time optimization, because then the compiler can see your entire program and it can provide much, much better optimization. Usually when you compile, if you're not using link time optimization, it sees one individual C++ file at a time, so it compiles each one individually, they all get linked together, and that's it. And because it can't see out, it can only see one file at a time, it can't provide optimizations between all the files. Using link time optimization gives you that. It still compiles them all individually, but it doesn't fully compile them. It emits this sort of intermediate output, and then when it goes to bring it all together, the compiler gets called again and given the entire code base.
So how can you recognize that this is done wrong?
Sorry?
How can you recognize that it is done wrong, the digits, what it is?
If you really, really care about that, the answer is disassemble your program. If you're that performance critical, then you need that skill. You should be able to disassemble it. There's Godbolt, obviously, Compiler Explorer. That's really working on a sort of one translation unit basis, one CPP file equivalent. So you can at least see if within a single file it will work. But if you want to sort of verify your LTO is really working, disassemble it. Not an easy answer, I'm afraid, but realistically, I mean, that's it. You've got some output. The only way you can know if that output's what you want is by looking at it, and the way to look at it is disassemble it. Right. Slight change, still I think related to RIP. We're going to talk a bit about software architecture, and again, a quote. I've combined two quotes in this. You're getting two for the price of one. If all you have is a hammer, everything looks like a nail, by Abraham Maslow, classic quote, I think everyone knows, but then my favourite one. When your hammer is C++, everything begins to look like a thumb. Steve Haflich, that's great, I love it. So, let's just have a little chat about, well, sort of skill levels really, and what you should expect to be expected from you as you progress through C++. So as a fledgling programmer, just try and get your code to actually work, right? The best code is arguably the correct code anyway. So if you can at least produce something that's working, well done, great. You're probably going to struggle with reading APIs, like libraries other people have written and specifications, but that's okay. You're just starting out, you're beginning. Don't worry about that. But then you're probably going to become more confident. No, it's okay. You'll become more confident. You're going to be tweaking your code. You've started to understand more of the language's syntax, more of sort of how it works. You're not fully fluent in it necessarily, but you've realized well, maybe I shouldn't have a function that's 2,000 lines long. I can break that up into other functions. You start to understand just how you can sort of make your code a bit simpler, even if you don't necessarily even if you haven't necessarily mastered the entire language. Documentation should be a bit less confusing to you. You can hopefully write some of your own even. Maybe you start using comments a bit more. Maybe you discover that actually writing tests for your code is great. You do some code, and you just write a little bit of code just to test it, make sure it works. It's something automated so that when you add a little piece, you can just run that test again, see if you haven't broken the test. That's cool, because now you've captured the behavior. And then you get a bit better. You start thinking about the design and structure up front. You become comfortable with the language. You know that, well, I can turn this into an interface, right? And then I can have this implementation down here and this implementation down here. You start to think of your problem in terms of objects. So you can naturally say, oh, well, I think this should be a class, that should be a class. And as I just said, really, yes, you can rationalize about OOP. You can really actually design a nice piece of software. But you've also discovered that writing tests before doing an implementation is actually platinum. The platinum standard. You've gone from the gold standard to platinum. You don't even write a line of implementation. You write a test first that describes what you want. It doesn't have to be a big test. It could be a small test. Then you go and write the implementation to satisfy the test. So you've only written as much code as you need. If you need more stuff in your implementation, you first write a test to give you a justification to write that implementation. And good designs. You've realised that a good design comes from trying things out. It's not just simply sitting there with pen and paper and thinking, oh, I'll just make sure I've got everything designed up front, I know it's 100%, and then going and writing it. No. You actually go and write code that you fully expect to throw away. You just try things out. You only gain experience by doing that. That's how you've really come from here to here. But because you've now learned that, you're comfortable doing it. You're not trying to get it right first time. You know that having a good design comes from actually just experimentation and throwing things away. And then finally, you reach the level of software architect. And you stop writing any code, you fall out of practice, but you still pretend you're an expert because you want to collect that paycheck. But no, I'm just joking, really. Only bad architects sort of fit that bill. Even if you get up to software architect, you should still be writing code. You should be keeping up with the standards. So, but there are people who, they get some sort of tenure or whatever and they just give up. Hopefully that won't be any of us here. So, growing your skills. A key point is write code and write it often. You can no more learn to code C++ or any other language than you can learn to play the violin by studying what material it's actually made out of. You need to write code in order to get good at producing code. So because of that, we will shortly be delving into a little mini project, which I've set up for you. I will be giving you a complete specification. You'll have everything.
Are you sure?
Well, you'll either have everything, or you'll have me to give you corrections.
There's always complained about specs not being complete and asking more questions. So
we are live on YouTube, so if there is anything that I happen to have missed out, because I am human, then I am here. Please ask. It's up to you.
Meeting, you can have the answer in 2 weeks.
Yeah.
If there's anything missing from the spec, we'll schedule a time meeting.
Yeah.
If there's anything missing, it's called a functional spec.
Yeah, if there's anything missing, it's a functional spec. Well, there's a quote coming that's gonna work with this. At least I think there is. Oh, maybe not. I used it yesterday. It was that what was it? Software and skating, ice skating are easy when both are implementing software specifications and ice skating are easy when both on a pond are easy when both are frozen. Anyway, so it's up to you to decide how much of the spec you want to do or can do. And I've tailored the task to allow you to make this decision. So there are different difficulty levels that you can choose. And don't be afraid to go up or down in difficulty. If you don't feel confident, you start on easy, but then you realise actually this is not bad, just stop and go up one. And you will end up with a working application. This is something you can show to other people. You have it on your GitHub. You can say, look what I made. I made a little game. Hooray.
I follow this.
So it's noughts and crosses. And a wonderful quote by someone who in fact works for us is our Chief Science Officer, Nathaniel Borenstein. It should be noted that no ethically trained software engineer would ever consent to write a destroy Baghdad procedure. Basic professional ethics would instead require him to write a destroy city procedure to which Baghdad could be given as a parameter. I should also know that he is a pacifist. So, implementing a game. Yes, we're going to implement a game. So, start taking notes here, folks.
Oh, we have to actually take that.
Well, okay. So when I say there is a complete specification, but I will be providing you some sort of pointers, not the kind of pointers you get in C++, of course, but some advice perhaps. So the game Noughts and Crosses, aka tic-tac-toe, is reasonably simple. Does everyone here know it? I suppose maybe there's someone online who's never encountered it. So you have a 3x3 board, right? A grid. One player is the X, the other player is an O. And they take their turns to place their symbol on the board in one of the cells. And you win by connecting your X's, or if you're O's, then the O's, together vertically, horizontally, or diagonally. And this is, in fact, a solved game. This won't really matter for this lesson, but we'll come back to it. A perfect player can guarantee at least a draw, no matter who goes first. So if you have two perfect players, two AI, for example, that have the algorithm, they will always draw. There will never be a winner in that case. So, as I said, they always win a draw. So the first thing we want to do, because this is C++ and this is about OOP, we want to model our objects. So, fairly obvious one is there's a board. You want a board class. You're going to want a class to represent the board. Class, struct, whatever. I use the word class. Because the game has a board, right? There's nothing that's going to be a kind of board. There's only one. So we just have a single concrete class for the board. Now, if we were doing TDD, we may want to interface it away just for mocking it, just for plugging in fake implementations. But we're not going to be, I'm not expecting that of you. Well, unless you want to do pro difficulty, then please feel free. But yes, you might want to interface it for mocking. And of course, we also have players. And again, there's only 2 of them, but that's fairly generic. And we'll just compose them in something else, in a class that manages them. So there are, however, potentially 2 kinds of player, right? We have a human player, and we have a computer player. So it makes sense in this case, we will have an interface for player. Also because it's just good practice. I think anyone who did exercise 2, the exercise last week, should have created an interface. So again, it's just good practice in any case. We will need a renderer class to handle displaying the board, right? We need something that can actually, display it on the screen. But fortunately for you, I've done this for you. I've created an implementation. I've even given you an interface for it. So you don't need to know anything about my renderer implementation. And there's a good reason for this, actually, because I could write a full... So currently the renderer I'm giving you is just on the console. It will just print to, the text-based console. But later on, I could make a GUI for it. And because you only know my interface, when I eventually get around to implementing that, I can carry your code can carry on working with the interface. And I'll just give you the one that does a proper nice GUI instead. And of course, we'll need a controller class for handling the game logic, right? It needs to handle players taking turns. And I would say that you should worry about calculating a win after you've simply got it to just let players take turns and fill a board up with squares. Don't necessarily initially worry about it saying, oh, stop, somebody's won. Just worry about getting it to actually fill the board up. So let's just sort of summarize the game and in the context of those classes we're going to want. We need to write an I player, the interface. I put an I in front of it because it's obvious it's an interface then. So if it's I and then a word, that means it's an interface. You don't have to do that. I recommend it. Sorry? That's an uppercase I, not a lowercase I. In this case, not in their case, it's lowercase. So this represents a generic player object. Also, you wouldn't have to do this. If you want to go and rename it, you can, but I'd say just stick with the names I've put in there for you. We have a human player, which is obviously a kind of iPlayer, so it will derive from iPlayer. This will take some input from the command line. Obviously, the player is going to need to choose which cell they want to actually occupy. A class for the board. The board will represent that 3x3 set of squares, and obviously track whether a cell is occupied or unoccupied, and obviously who it is occupied by. A controller tracks obviously the game's state, right? It will tell a player to play. Once you've filled in all the squares, it will stop because you've run out of squares. And ultimately, eventually, if you feel up to it, it will check if somebody's won. And of course, it will also update the board. It will tell the board, okay, this person, it will call the player and say, what square do you want? this class will return and say, I want this square, and then the controller will take that message and call the board to say, okay, please occupy this square from the one the guy wanted. And of course you need a main function. The entry point, right? The operating system will call this function to start us off. So in the main, we'll just construct 2 instances of the human player class, because we've got 2 players, 1 instance of the renderer class, 1 instance of the controller class. And then the controller class really is the thing that's bringing it all together. The controller will take both of the references to both of the players and the renderer, and it's going to coordinate everything together. So let's just quickly talk about the board class. Probably should have put this in front really, but the board needs to track the state of the board. Right?
Isn't the board the state of the game? Except the controller, you've got a controller class.
So the question was.
If you go back one
Yeah, sure.
slide.
That's it.
So you've got board representing the 3x3 board, tracks occupied on occupied side.
Mm-hmm.
But the controller tracks the game state.
Yes.
Now surely the board's implicitly got the game state.
Yeah, you could. I suppose that's valid. It knows.
The state of the game is more than just the board, as you were talking about.
Yeah, I mean, so the board
logic
knows.
Is in the controller.
So yeah, the logic's in the controller. The board just knows the board, right, and the organisation of each cell. You could obviously merge it into the controller, but there's a reasonable amount of code that needs to be implemented just to have a board. So my feeling was that it's better to split it up a little bit more and have a board. Also, just to sort of teach your OP, the idea is don't be afraid of having more objects, right? Especially when there literally is a board, right? A board could be used for anything as well, right? Why should the board necessarily know about the rules of the game, right? If I've got a 3x3 board, I could use that for some other kind of game, some other different set of rules, right?
Well, that's what I was sort of getting at. Is the board just holds the state whether it's not empty X or 0.
Oh, I see. Yeah.
And then the controller is just purely the logic.
Yes, but you're thinking, yeah, but so in this design, the board will be a bit more generic than that. It's a 3x3 board, but you could use it technically for anything, right? It shouldn't know the rules of the game, right? The controller knows the rules of the game. So yes, the board class, it needs to track the state. It just have a default constructor, and when it's default constructed, it just marks every cell as unoccupied. Obviously, it should have some kind of private member data for each of the 9 cells. It's 3x3, and it should have a function that returns a list of unoccupied cells. Again, a lot of this is captured in the specification, so don't worry too much. It can be context accessible because obviously returning a list of unoccupied cells isn't going to modify anything. You want a function that can be used to tell the board, okay, please occupy the following cell. And obviously the controller is going to use this to tell the board that, okay, the player wants this cell. If somehow, you accidentally manage to make it give a spot that's already occupied, the board should not allow you to do that, right? Indicate an error. If you're familiar with exceptions, feel free to throw exceptions. If you're not, just print something out, print something to the screen, print an error, right? And it should also have a function that just returns the state of all of the cells, right? I just want to be able to have all of them, and of course, I can use that. You can use that in the controller, so that you can tell the renderer what to actually pump onto the screen. So the iPlayer interface. This will be only pure virtual functions, of course, because it is an interface, and this will apply to everything I'm going to say below. So we should have a function that returns the player's symbol, an X or an O. Strictly speaking, it doesn't matter what you want to use. Preferably just stick to X and O, of course, but it can be flexible. This again can be const accessible, so you'll have the interface function will be something const accessible to return the symbol that the player has. And of course you want a function to tell it to take a turn, right? So the function will need to be told what positions are available, and then it can return which one it wants to occupy. So my human player implementation will also use that data. The interface is just declaring the function. So in the human player implementation, which obviously derives from iPlayer, we'll take a constructor, which will tell us which symbol to use. Obviously pass it an X character or an O character, or a capital O. Store this as a piece of private data, because you're going to need to hold on to that information. And then the symbol override, of course, will just return whichever symbol it was given in the constructor. So that's of course why you need to hold on to it in your private data. And then you obviously need the override for take turn to tell us, okay, it's time for you to take a turn. And then obviously, first of all, we need to use the argument we get. So I haven't put the arguments in here. So there, it does take an argument. I've just abbreviated the function. You use the argument, of course, to tell the player, well, this, and this is available. When I say tell the player, I mean tell the person sitting at the keyboard reading the screen. You need to tell them, this spot is free, this spot is free, this spot is free. Which one do you want? You can take position 1, position 2, position 5, whichever one. So you need to be able to tell them that, so you can then allow them to type in on the keyboard which number they want. So you get the input from them, from the person, the human being, to see which space they want. And then you just return that, of course, once they've given an answer that was legal and valid. If they put 99 in, then obviously you shouldn't just return that. The controller class will, of course, coordinate the game. It knows the rules of the game. So, of course, it should have a constructor that takes an iRenderer, which again, I've provided the renderer for you. It will print to the screen, does all that nice stuff. Prints the board for you. So it will take one iRenderer, and of course, because it's an interface, you must use a reference or a pointer. It's up to you which one you want to use. I would suggest an interface, but it doesn't really matter. You'll need to give it 2 players, so 2 iPlayers, of course. For this exercise, for this little project, they'll both be human player. We're only implementing human versus human. If you want to go off and have a computer player, feel free. And of course, just store them in the class as references, and privately in the controller as references or pointer members. And of course, then you just want to play game functions to kick everything off. And of course, once you do call play game, it doesn't return until the board has been filled, or once you get around to it, someone has won. And then of course, our main function, which I'm pretty sure I already had a slide for, I must have duplicated, but yeah, so hopefully everyone knows what int main is for actually. Is everyone clear on int main? Hope so. Yeah, cool. And of course we can have a simple one. I duplicated the slide somehow. But yeah, you construct the human. Oh no, wrong button. Wrong button. Hold on, it's coming back. Construct the human player, 2 human player classes, pass the X or O. One is X, one is O. Create the my renderer, which I've already given you. Don't need any arguments to my renderer, it just works. Make a controller, give it the 2 players and the renderer, and then just call play game to kick it all off, and done. So, to tweak the difficulty to your taste, I've given you a few options. And now I don't mean the difficulty of the game, I mean the difficulty of actually implementing this project. So firstly, there is a header called utility.h. I've commented it. Please read it. Please read that source. You don't need to read the source, but do read the comments. They explain how to use it, what it does. You don't have to use it. If you know what you're doing, then feel free to ignore the file, but it's just there in case you want it. All of the functions in that header have comments explaining what they do. They're just there to make your life easier. Don't worry about the source code of them. Just read the comments. It tells you what they do. So the Git project has multiple branches that you can start your work from. We have a branch called Easy. You only need to implement the board and human player, and that's it. I've done everything else for you. So all that stuff you just read, you don't actually have to do. We have Medium. The controller has been fleshed out with some data and hint functions, but they're empty. I've just given some suggestions on design, effectively, but they don't actually contain any code. You still need to do the code yourself. Board, iPlayer, and human player are just completely empty files. And we have the Tom difficulty. This man here, the hard difficulty, realistically. Which is, I named it Tom because if you don't do it, you failed. You failed me. You must implement everything from scratch except for the render, which is obviously everything I covered in the slides. No pressure, Tom, no pressure. And then there's Pro. The Pro branch is literally just a README with the specification. There is nothing else in there. If you want to go for that, please do. And if you want plus points and impress me, do test-driven development or behavior-driven development. I'll be well impressed. Right, so let's get started.
What if you implement machine learning on it?
I'll be really, really impressed. So as usual, so please go to this link. I will be posting it onto Slack shortly, and then Tom can copy it to GitHub. I have a slight problem, Tom, because I can't see my mouse. So if you could do the honours, please do. Oh, I cancel the mouse.
Does the renderer just give you X and zeros in a sort of ASCII text format?
Sorry?
Does the renderer just give you sort of like A grid of 3 by 3 with a
Yeah, just print.
X and 0.
Yeah, try it. You can call its API and see what it does. The default difficulty is medium. If you need help switching branches, there's 2 ways to do it. C Lion or Git checkout. And yes, there is a solution branch, but preferably please just ask for help before you give up. And I've also made it more complex, so don't try and copy the solution branch. I've deliberately made it more complex so that I'll know that you have.
How much time do we have to complete that?
36 minutes. Sorry.
No, you don't have 36 minutes, obviously. This is somewhat something
I think we normally push for 36 minutes.
Yes, this is somewhat something to take home or come to the workshop on Thursday, preferably, and work on. If you were to implement the easy one, you might be able to do easy difficulty in half an hour.
Okay, another question, bearing in mind
Yeah.
there's so much attention and weight on my shoulders right now. If you try the easier one and then you retrace, is that like can you let's say we use the same code?
Yes, I see what you're saying. Avoid, if you do want to do the easy one, avoid looking at the code that I've done for you, right? Avoid looking at what I've implemented, because otherwise you would just...
Here, I'm just trying to understand, so for example, if I, let's say, try...
Yes, that's what I said earlier, right? Don't be afraid to go up or down a notch. If you start out on medium and it's too hard, just go down to easy. If you start out on easy and it's too simple, go up to medium or hard, right? Just feel free to switch as you go. Save your work, of course, right? Make sure to save what you've done if you want to keep it, but you can always switch branches. And again, if you don't know how to switch a branch, instructions are here, or just ask me, I'll show you how to switch branches.
Yes, sir.
And of course, don't be afraid to ask for help with programming. My number's there, but I'll try. Right, we got mine. I mean, we got the telephone. I got mine.
Oh, yeah.
So yeah, so you have the numbers. You can put out my phone numbers on. I'll go down there.
Was that good?
Did it come to these things you remember my
No, I wasn't coming to the first one was your first week when we had those people from 70 odd people. That was
we've been going a while now.
yeah. So that was the first. That was when I.
I know you're one of the old times.
I'm still don't know what we're doing.
In terms of how long you've been coming to these sessions,
Yeah,
that's
exactly.
right.
Not knowing what we're doing. But this is quite exciting.
I'm just opening it.
Not too bad, I'd say.
Okay, fine.
Any further?
Reading.
Yeah, I mean it wasn't too hard to do.
Well, you know, it's like it was working, but on some part it deleted the channel in his pocket and then this person coming out. And something that should be easy, like working 6 or 8 hours while before, because I was playing changes like no, it doesn't see. Like I only interpreted your words, but like you said, it doesn't, it's not passing, and I read it, it doesn't see the class. And I was clicking, like when you have this connector says it goes from one class. No, it's fine, it's fine. Yeah, it's fine. I figured it out, and it took 6 hours or whatever.
It's always, it's sometimes a bit hard to just have to wait.
Justin, do you know what? Do you know about this?
I don't know what.
Well, I thought I'd have a go at the pro. But it's got all this code in it still. Controller, board, well, I should have the spec actually. Give it a go.
Tom Brown emergency so he was just being really nice. Some programs he did.
I'll give it a go. It's quite exciting personally.
That's the one.
processing you're running your
Yeah.
They're not coding. It's done this before. For some reason, it takes a long time. What you can do is you can go to CPP underneath GitHub.com/CPP, and that will have the top repository on there will be the just code that one. It won't like copy it to your own GitHub. You won't have your own.
Yeah. Well, it started with that's all right. Don't need much more than that.
I should have done that the first time you installed it.
It's good one. I'm always doing that. That's the one. That's the other one, isn't it? That one. Yeah.
It's brand new laptop.
That's it. No. I did a Suzuki. So what I did is Suzuki.
Just create a test project.
Yeah.
Yeah, project name.
Yeah, just project name and then all the files. All the file. I just add all the files that I have in my list. Basically.
Okay, you've got Visual Studio installed.
Probably already read that badly.
What else do I need to put in? Which version of Catch do we do?
The latest?
That's what I think. So you can use Visual Studio. Sorry, you can use
Version 2.5.
Studio Compiler. That's like the latest experiment. It seems to work right. Or you can download the GCC compiler. And we recommend that because GCC compiler is a bit more. But if you've got the option to use both, that's even better because you tested code and compilers. So what I'll do now is it's okay. It's not better than it used to be.
He's going to be on that.
Some people like, okay, great.
In general, we prefer to use C-Line because everybody's got the same thing. Because I don't use Visual Studio. I've got a Mac. Some people use sea lion, but not everybody's on the same page. So I don't necessarily to use Visual Studio.
So you'll be able to use Intellijator pretty easily as well.
Is that the Java?
Yeah. Or PyCharm. Or Rust.
They're all basically the same. Okay. Well, just downloading GCC.
Shade.
It's a challenge now.
No, definitely.
By the way, Tom, I hope you're working hard because 10 minutes we're expecting your presentation.
I didn't even manage to read through the specification. I'm slow on uptake.
You don't have to read the whole thing first. You could do one class at a time, if you wish.
Okay, question, because I'm trying to, with just readme file for now, yes? Where should I be, because that's not obvious to me, where should I be keeping
You know,
my...
it's better if you read this rather than this.
I don't like this for whatever reason.
How long do we have to do this?
I don't know why.
Obviously, I'm not. It's part of the lesson, so I'm not forcing anyone to do it. If it would be nice if you would complete it. It would be great, and I'll be happy to review it if you do.
No, we have our own time.
Yeah, you take the time. Absolutely take the time. You're not expected to complete this now.
So,
No, I know.
where would I keep my classes and so on?
So there's no. You can if you. If it takes you a month to do it, I would expect it to take you maybe a week at most. I did this in a night.
Yeah, no, we're not.
Yeah, by your prop.
And that included thinking of the design. I would say a week, but there's no actual time frame here. Okay, if you need to take a month on it and then get it reviewed, just work at your own pace, get it done. But see it as a personal project, a personal challenge to get this done, no matter how long it takes.
Question, so which one I can look into, which one I should?
It's difficult to you.
I'll try with the Pro and I'll drop to Tom if I find it, but I can't do it.
You're not on Pro.
I'm not?
No, defaults to medium.
Okay, so what they do, you go to branches. Check out this.
There you go.
I'm going to change my mind. So,
So each one of these main headings is actually a file.
There are just, I just think this one's quite good, quite easy to install.
What files you need?
Board. No, I'm giving it a bash myself. But just to get the structure, you see that each one of those is a header file. It's a class. It's a class, but you generally put each class.
Change all H.
Yeah.
I'll tell you there. It's even found one.
So generally, it's a good rule. Each class has its own source file. Yeah. Okay. So it's a declaration or a definition for each class.
Okay.
Cool. No, this is quite exciting actually. I quite like it. It's good as I like a project like this. This is what it's all about actually. Yeah.
You want to learn to code? You got to write code.
I was just getting a bit bored with the code stuff.
So I should be creating on a Pro. I should be creating the info folders, source folders like you do here.
I mean, you can do it however you want. The point of Pro is
Get on with it.
doing.
Get on with it. You've got to start
You can
programming.
do that. Do it your own way. The point of Pro, right, is you're a pro. You can just do it. You don't need to ask questions. You just go.
I know.
I mean, you can ask your questions, but I'm saying that if you're doing the pro difficulty, really, you should just.
Because I mean, where I'm coming from is I'm trying to make sure that my understanding, of the instruction, is, let's say, so I don't diverge too much from what you.
So if you are on pro difficulty,
So you get
treat the specification as a general suggestion of how to implement it.
Okay.
Obviously, if you implement it, it's not in any way that you implement it. It's one function. It's one line, one page. animation fail, you don't have to, if you're doing a pro, you don't have to follow what I'm saying.
Okay.
You're free to come up with something better. Maybe you're already clever and you can say something better than me.
Add two numbers.
Okay.
But
Exercise one. Level
you
one.
can't use it. Probably might be a bit much.
Yeah,
Pretty right.
No, no, I'm understood.
Yeah, yeah. So just give it so you have.
I know we get set up with it now.
I'm level 4, so I'm
Because like I say,
halfway.
you get a month for free.
I've been playing around.
For those of you still watching on YouTube,
This is yeah.
please don't forget to tell your friends about us, and maybe consider supporting us on Patreon. And of course, if you are on YouTube, you can always get in touch with us through the Slack. And if you need help implementing this, we are always on hand.
You have to pass the test. No, you have to pass the test. You have tests. So, for example, if you have so for example, if you have this is one I was really struggling with. This is the hardest one I ever tried. You might be interested in this one. Area of Veroni cells. This was the big project I was working on. You've got to work out the area of each colour's box.
Area
Oh yeah, really? I'd like to see your solution, mate.
Do you know the size?
No, absolutely. All you know is those black points. That's all you know. That's all you know.
What are the black ones?
They're points.
Imagine you ignore the coloured things for a minute. Imagine you're given a black points. You want to construct the nearest neighbour polygon.
So you can't put it.
No, then you need to work out the area of each of those irregular polygons.
I'm sorry?
Oh, okay. But that's real.
Yes, I think you're right.
The one I got was really interesting. Was this the one was it was similar to this. It's called a battleship. You got a battleship. Yeah.
So you do that one?
Yeah. It's to do solution validation.
So you completed the battleship?
Yeah. I'll just show you. Battleship. Connect forward to the one. I think that was quite interesting. Battleship validation. That was level. So basically, write a method takes a battleship. You've got to work out whether it's a valid battleship. Two cruisers, three destroyers. And they're not in a kingdom. They're not next to each other. But I tried to do it in this this was my solution. That was my solution.
So you're giving some imaginary access.
You just check the object file. I tried to do it with object, so this is the main code.
I think it's which branch
This is I tried to do it with object-oriented programs. So this is the main code.
Yeah, so if I try to file, it's empty, and anything gets there.
Can we find battleship? Can we find two cruisers?
So I need to create my own layer, check the cache.
And then that goes in each of my classes up here, each of my does
So basically what I'm creating
So it's always
putting this stuff here under
that's much better than this. And that's a really interesting one if you want to try that. Battleship. If you like the code, that's you start with level 8. I quite like doing But that I must admit. All the time. So folding an array, that was interesting.
Yeah.
That was
So I need to see here executable, yes, that is correct. But if I'm doing the test, so
That's
like,
quite easy.
the outcome executable.
Basically, you take that.
So I'll be doing this.
And then you fold it over.
Then which they are.
So you flip 4 or 5 and you do that as many times. It's just showing what it does. Yeah, yeah. That's
Source.
That was nice.
But then I don't make
That's only
like, so it's only this, so it's
especially do that, take me a couple of days. That was the one took me over. No, it's a couple of hours. Probably take Ollie a second. This was just saying, this code one, I think code was a really good idea.
Good idea, yeah.
So I'm just, this one was folding an array. Yeah. So it's quite an easy one. So,
Well, of course you can't run it in this environment though.
yeah, well, no, you take it out. Like you want to test it with your just and then just paste the code back in.
Yeah.
And so
You want to break.
yeah, but you could do it. I mean, for example, I did a battleship validator, and that was all done.
Yeah.
I was running the same tests.
Oh, you use
I just copied their test, but it added some on some of mine. So this was a nice one. This was quite a nice one. This is just folding an array. So just folding it about and then as many times as it wants.
Your what version C++ only standard C++, yeah, you can use range. Still.
So and it's interesting. So
Like folding the numbers in an array like this and adding them together.
without but yeah.
Nice.
Well, I'm trying to not use that one. I think I'm trying to not use Zeus. I'm trying to use the SQL.
Oh, I see that. Yes,
Because that folding that array was really easy to do in a loop.
Yeah. I mean, that's pretty.
So, you know,
I mean, it's not you, obviously, but
but it's interesting to see what some other people have done.
Wait.
Can you see it?
So you can see that.
Do they show you that one?
If you solve it yourself, when you solve it yourself, you're going to have other people. That's fine. That's fine. What did I do? Prepare my So, but once you do, that's your learning, isn't it? You know, you do your stuff. You spend 2 pages doing it. Some smart art's done it in 1
Was it a fixed size slope or any size?
I think.
Second.
Yeah, you have to fix it. No, it was a Sudoku one. I don't know. I think it was any size.
I know you can do them online, just throw everything in
And the toilet set. Sources there.
I'll come around. I'll be around.
But anyway, so some of that. But you should try it. It's really. I think it's really good. It's interactive. I've done quite a lot. So yeah.
Do you your things from them?
Controller.
Well, you do whatever you want. You can do whatever you want. You I mean, so I took that as a phrase for the try and do. Try and get to one line.
Can you get the switch?
Some, if you feel really, so some of the easier ones, you can, yes. No, one, that was that. It's generally not. But I don't.
You've already done it.
No, I'm just starting the scenery. I need to control this. I need to as well the catch, yes. So I need to update here. So that's going to be my catch. Correct?
I mean, if you run it,
the ones who are using the SQL.
yes.
That's how I wanted to learn.
For now. I don't want to like do exercise.
So what's later with the code stream?
I can learn the C++ while making
So I don't have here, I'm not having catch here.
What game?
because I already know C.
What game?
Oh, that's that fine. There's this pay to win that I have that I've played. I think I've visited and normally the people who play this game and they have jobs and they lose money, they spend a lot of money.
Yeah, but that's quite difficult.
You win a lot of things.
Yeah, you have to start with something else.
Like this?
That's the key. Whatever you do, you have to do it. It's nice, but I wrote it.
You roll up, yeah?
Yoga.
So what, just you
A little man doing yoga poses. And it, yeah, it talks to you.
Talks to you as well?
Yeah. It's good use the text to speech.
text to speech, yeah?
Yeah, you can just, if you go into Chrome, you can just say the file straight out.
So you hear like this robot?
No, it's got an Indian accent. I show you, I haven't got my phone.
That's cool. So it's free, yeah?
Yeah.
You should like improve us now. Okay.
I've made
So-
35.
You made it back up?
Really? That's not very good. Not very good. It was not cost effective. You only make money on Google Play. Forget it.
Or if you have like
They won't buy it unless they know about it.
That means if someone doesn't know it exists, how are they ever going to buy it? Because they'll never find it.
The way to get it, you have to have, if you want an app to do well, you have to have a massive advertising. You can write the best app in the world, Android app in the world, and no one knows about it.
It's like you can be the best guitarist in the world. No one knows about you. You know, you're amazing at guitar, but nobody knows who you are. So you just
And there's companies back going on.
Is your ads that good though? Is that good?
No.
So if it was that good, maybe you should actually design just something like that.
Nah,
So basically what this like
I
got includes as a
Sorry?
Mm-hmm.
No, that's the whole thing about it.
because you've got target directories and contain
You can make your own samples, and then it goes through. It doesn't move like a person. It doesn't move like a person. But it actually goes into your post, and it gives you the sound that you post. That gives you some of the you can make your own patch. It's got about yeah, it's got Series A. It's got some standard versions. I put in a standard Series A.
The building.
Yeah, vinyasa stuff. So the standard has a Series
Are we finishing?
Give me a couple of minutes.
I did have
Or actually, no, I've got to do it at the end. Fuck. Yeah, okay. Shall I wrap up? Can I, what I'd like to do is, if you let me wrap up quickly, disconnect my laptop, while you're rounding off, I can have time to collect my shit and clean up a little bit. Make sense? Yeah, cool. Okay, right everyone. Thank you very much, but once again it has, gotten to that time. As usual, thank you, for joining us. I hope you found it informative and you're enjoying the project. As usual, we're going to head around the corner to Beer Schenker if you'd like to socialise with us. And as ever, if you'd like what we do, please consider supporting us on Patreon. And I will now hand over Tom to echo what I've said mostly, but round off.
Okay, so